Hello everybody, my name is Sarnath and in this video I am going to take you through the Fisher exact test. You can see the picture of young Ronald Fisher here. He is the one who designed this test, and this test is used to establish statistical significance. For example, you are a marketeer and you did a marketing campaign. So before the campaign you had your treatment and control group, and then the marketing campaign was rolled out only to the treatment group. At the end of the campaign, you want to know whether people converted more in the treatment group than the control group, right? That is a case of working out percentages. You can easily figure it out. And after figuring it out, let's say that the treatment group's conversion rate is 36.2%, whereas the control group is 35%, right? It's 1.2 percentage point change. Now, is this 1.2 percentage increase, big enough to be called as a lift generated by your treatment, or is it some random variation, right? It could be a random variation, right? So we want to know that. So to do that, we can use this Fisher exact test. And in this video, I will not only show you how to use this test, I'll also show you the background motivation of this test, its relationship with hypergeometric distribution, how to compute this test in Python. I'll show you Python code to do that, and I will also show you Python code in which we can execute this test manually, right, using the hypergeometric distribution. And I'll also show that in both the cases we see the same result, right? So without much ado, let's proceed. Let's say that you have done a marketing campaign and the results are as shown in the picture. So out of the 1,800 people in treatment, 100 people have converted. Out of the 3,050 people in control, only 50 people have converted. Okay, so we work out the conversion rate. The treatment happens to be 5.55% and the control happens to be 1.63%. And to my naive eyes, it's significant. Like, treatment is good, it's a lot better than the control, but we want to mathematically establish that. And to establish this mathematically or statistically, we need to answer a question. We have seen an increase in the conversion rate, but what is the probability that such an increased lift occurs purely by chance, right? It is not really by treatment, but purely by chance. If we can answer this question, and if that probability turns out to be very less, generally less than 5% is considered as good. If it is less than 5%, then we say that, okay, most likely our treatment worked, right? So this is what people call as rejecting the null hypothesis or whatever. But always keep in mind that when you're rejecting the null hypothesis because the probability is less, it is still a probability, right? There is still a very less percentage that it happens by chance. It's not ruled out, right? So just keep that in mind. When communicating to business, you can communicate in different ways. I'll show you in the later part of the video how to do that. But as a data scientist, you should keep this in mind. So how do we generate this probability, right? So we only have 4 numbers. Like, what probability, right? It's confusing, right? So just take a look at this picture. Let's focus on the contingency matrix, the 100 out of 1,750 out of 3,000, right? If you take the entire population as one segment on the left, the green boxes, we know that 150 people converted totally, regardless of treatment and control. There are 150 people who converted, right? And then the people who did not convert is 4,700, right? These are the green boxes. Now you can say that from this population 150, 4,700, if I pick 1,800 people, what is this 1,800? That is this 100 plus 1,700, right? If I pull 1,800 people randomly, if I pull 1,800 people, right, what is the probability that I would get 100 and 1,700 split? 100 people who converted, those in this 1,800, the 100 people comes from the 150 group and 1,700 comes from the 4,700 group. Right? So if I take 1,800, what is the probability that I get 100 and 1,700 as a split? I could get 0 from the converted segment, and all 1,800 could have come from the 4,700, right? Because I'm randomly drawing, right? So if a random draw from this, what is the probability that it can generate this kind of a contingency matrix? right? That is our first step towards establishing probability and also statistical significance, as we will see. To calculate this, we can apply simple probability rules, right? Out of all possible 1800 combinations that can be drawn from 4850, if we can find out how many combinations have this 100,700 split, then we can work out the probability pretty straightforwardly, right? We can just take the numerator as 100,700 groups, number of such combinations, and then you divide by the total number of combinations, you get your probability, right? So to first establish how many such 1800 combinations can we get from 4850, right? So if you name the people as P1, P2, P3 until P4850, so the number of different ways you can get 1800 people is given by 4850 C 1800, where C is the combination operator. So we all would have studied the NCR is equal to n factorial divided by whole divided by r factorial into n minus r factorial, right? That is the combinations operator. So 4850 factorial whole divided by 1800 factorial into 4850 minus 1800 factorial, that is the total number of unique 1800 combinations that you can generate from 4850. So that will be your denominator. And what should be the numerator? The numerator is 100 coming from 150, how much such combinations exist, and 1700 coming from 4700, how many such combinations exist, and then you just multiply them. Why multiply? Because they are completely independent. Each combination from 150 C100 can be combined with each combination that comes from 4700 C1700, right? So you just have to multiply that 150 C100 multiplied by 4700 C1700, the whole divided by 4850 C1800. So that will be the probability of generating a random sample that has this 100,700 split. So I have listed the formula for the probability that we saw just now. The square brackets here in this formula represents the combination operator. So when you see this 150 and 100 inside the square bracket, it simply means 150 C100 multiplied by 4700 C1700, the whole divided by 4850 C1800. That is the probability of getting this 100,700 split when we just take a random sample of 1800 from 4850. Right? And this happens to be the basis for a distribution called as hypergeometric distribution. We will see what this is in the next slide. So in general, hypergeometric distribution can be looked at like this. Let's say if there is a sack of 400 blue balls and 500 red balls, okay? So it's like it has 900 balls in total, and from this, if you're going to draw 200 balls in random, right, without replacement, okay, if it is with replacement, that's something else. I'll cover that later. So without replacement, if we draw 200 of them from the bag, what is the probability that 50 out of the 200 are blue balls, right? So that is the probability of 50 for this distribution. So if we work out what is the probability of 0 balls being blue, probability of 1 ball being blue, all the way until probability of all 200 balls being blue, then that represents a probability mass function of the hypergeometric distribution. That is the actual distribution, right? It's a discrete probability distribution. As you can see, there is no e power x formulas, thankfully. We just have a simple discrete probability distribution. That's fine. So in such a case, you can see this formula I have written there. The PMF of 900 is the total number of balls in the bag, right? And 400 represents how many of them are blue, and 200 represents how much we are drawing from it, and this represents the parameter of the distribution, okay? And the distribution is evaluated for 50. 50 is the point at which we are calculating the probability mass function, right? So the 900, 400 and 200 are nothing but parameters of the distribution. So the formula is very simple. we have seen this before. So 400 C50, right? Because 400 is the total number of blue balls, and we can take 50 balls in any number of ways from that. So that combination multiplied by, we are taking 200 balls, right? So we have to take 150 from the red balls. The number of red balls is 500, which is 900 minus 400. So from 500, how do we take 150, right? So this is the combination in which we will have 50 blue balls and 150 red balls. These are the total number of combinations, and there are 900 C 200 ways of drawing 200 balls from that. So you divide it by that, you get the probability. So that is your hypergeometric probability mass function. So if I draw these balls with replacement, what happens? So if that's the replacement, every time I draw a ball, the probability of it being blue is 400 by 900, which is 4 by 9, right? So it's always the case. So if I draw 200 balls from that, then the probability that we have 50 of them as blue is nothing but your binomial distribution, right? So that's nothing but 200 C50 into 4 by 9 whole power 50 into 5 by 9 whole power 150, right? That is your binomial distribution. So when it is done without replacement, we get the hypergeometric distribution. That's it. So if we apply to our treatment and control, this is how it looks like. So we have a bag full of 4,850 balls, out of which there are 150 blue balls and hence 4,700 red balls, and we are drawing a sample of 1,800, and we want to know the probability of 100 of them being blue balls. That is exactly what we are doing here, and this is how the hypergeometric distribution applies to this treatment and control calculations that we are doing here. Here is a small plot of the hypergeometric distribution corresponding to our case. Our case is like there is total of 4,850, out of which 150 are blue balls. We are taking a sample of 1,800, and for that sample of 1,800, how many blue balls are there? Like 0 from 1 to 150, we worked out the probability and we have plotted it here, right? So that is your PMF corresponding to our case. Okay, so coming back to our original question, what did we want to establish? We want to establish that the observation that we have in hand, is it statistically significant or not? That is, if I take a random sample of 1,800 from those 4,850 people, if I take a random sample of 1,800, and if a significant portion of this sample we are seeing greater than or equal to 100 conversions, right? Then seeing 100 is not a big deal. It's not a statistically significant. It's just any random sample can give us that lift, right? If that is the case, then it is not statistically significant. However, if very few percentage of the random samples are greater than or equal to 100, right, then that means that 100 is a very, very significant deviation, right? It's not a random stuff. Then our lift is most likely very significant, right? So that is how we will establish. Now, we don't have to do random samples and all that now. We already have established the probability mass function. So we just go from 100 to 150. We just calculate the probability mass functions of seeing 100 conversions, or seeing 101 conversions, 102 conversions, all the way until 150 conversions. Seeing all that, taking all that, we take the sum of all that, and then we calculate a number, the sum of all these probabilities. That is the probability that a random sample would be greater than or equal to 100 conversions, right? And if that number is too less, then we know that we are statistically significant. So that is all it is. So this just visually represents 100 conversions, 101 conversions, 102 conversions, all the way until 150 conversions. You can see that when we move from 100 to 101, all the 4 cells are changing. It's not just only 101 is changing, right? So all the cells are changing. You just observe what is happening. So the way I look at it is from 50 to 100 you put an arrow mark, right? From 50 we borrow 1, so it becomes 101 and that becomes 49. In the denominator it goes in the other way around. From 1700, it goes to the 3000, so it becomes 3001 on the right and 1699 on the left, right? So that is how it is changing. That is how the contingency table is balancing itself all the way until it reaches 150, where you have got 0 on the other side, because all the 150 you have come it's a part of your sample, right? And it's left with the contingency matrix like this. So you just go and evaluate the hypergeometric distribution for all these cases and add them up, and that gives you the probability that a random sample has greater than or equal to 100 conversions. Like a random sample of 1800 having greater than or equal to 100 conversions. Here is the Python code as I promised in the start of the video. The left side shows how you calculate this probability using the hypergeometric function. The right side shows how you can do the same thing using the Fisher exact library called directly. Right? I would advise you to pause the video and check what is going on. It's just very simple. You can code it yourself in Python and you can check, and both the cases report the same p-value, which establishes that the hypergeometric distribution is a fundamental base of the Fisher exact test. So as we saw earlier, the p-value that is reported for greater than or equal to 100 conversion is too less. It's like 8.4 into 10 power minus 14 or something. Is too less. That simply means that the conversion that we are seeing it's not due to a random chance. The probability that it is due to a random chance is too less, extremely less, which means that the treatment is having the treatment lift that you're seeing is probably most likely coming from the treatment or the campaign that we did. So good. So how do you communicate this result? So if your stakeholder looks like the guy on the left is a business guy, he doesn't understand null hypothesis, he doesn't understand hypergeometric distribution and all that, never mind, just tell them that the campaign worked, the project was a great success, and hopefully we'll all have our bonus this year. So that's what you tell them, right? But if your stakeholder is a technical guy, you basically tell them that the probability that a treatment effect is a random chance is very less, so we are rejecting the null hypothesis. It's most likely that our campaign is having an effect on conversions. That is what we tell them. So one last mention before I conclude is, why is this test called as an exact test? Why not just Fisher test, right? So if you look at this test, the way it is modeled, be it that random sampling logic, the combinatorics, the connection to the hypergeometric distribution, all of them have no assumptions in it. There are no approximations. They are just hard combinatorics, right? They're hard numbers. It's just arithmetic, right? So that is why the probabilities that we calculate are like exact probabilities. So that is why it's called Fisher exact test. But that is not the case with some other tests. For example, if you take chi-square test, there are some assumptions of normality, there will be some approximations and limitations, assumptions, something would be going on in those tests. So the probabilities that we calculate are not exact probabilities in those tests. Whereas in this test, it's an exact probability, and that's the reason why it is called Fisher exact test. If you guys like this video, I would highly recommend you take a look at bytepond.com from Martin. Some of the articles that he writes are they're more towards coming up with a simulation to illustrate a concept, and usually it has a clear problem statement and the solution build-up is pretty clean. I think you would enjoy the articles. They're very informative. So do check out this website if you're interested. And at last, if you guys like this video, please like and subscribe to my channel. I'll be making more educational videos down the line. So let's stay in touch. Thank you. Bye bye.